In this unit, we've been learning all about acids and bases. So far, the acids and bases we've considered have been what's called strong acids or bases. These are acids or bases which fall apart when you put them into water. So imagine that you have an acid, two separate parts of a molecule put into the water, then they fall apart. So when they always fall apart, that's a strong acid and base. You can imagine it like Lego pieces that easily fall apart in solution. On the other hand, we have a category of acids and bases called weak acids and bases. These are ones that don't easily fall apart. So they have two parts of the molecule and maybe sometimes they come apart, but most of the time they stay together. In this case, you could think about a Lego piece that had been glued to another one. Sometimes maybe it'll fall apart, but lots of times it's gonna stay together. So let's learn more about this new category of acid and base called weak acids and bases. In this lesson, we'll introduce weak acids, then we'll introduce weak bases, then we'll practice percent ionization calculations. In order to introduce weak acids, it's helpful to consider strong acids. So here's the strong acid HBr. And if I take 3 HBr molecules and I put them down into solution, what happens? Well, it turns out that they dissociate. They split apart into ions. So we get H plus and Br minus. And if I put a total of 3 HBr's down there, I'm going to get 3 H plus ions and 3 Br minus ions. We would say that the percent ionization here is 100%. Every single molecule I put down into solution became an ion. And that's very different than with a weak acid like HF. If I take 3 HFs and I drop them down into solution, then some of them will split apart, but most of them stay together. So maybe the first one becomes H plus and F minus, and then the other two stay together as HF. We would say this has a 33% ionization. Just 1/3 of the molecules have split apart. And that's the difference between strong acids and weak acids. Strong acids always split up, weak acids just sometimes split up. Let's look at the formal definition. Strong acids are acids that fully dissociate in water. An example would be hydrochloric acid, which you see in these glass bottles on your right. You would find those in chemistry labs. On the other hand, weak acids show up in everyday life, like vinegar, which is a weak acid, and they're acids that sometimes dissociate in water. Okay, that's weak acids. Now let's talk about weak bases. Again, to understand weak bases, it's helpful to compare it to a strong base. Here we have sodium hydroxide. It's a strong base. If I take 3 sodium hydroxides and I drop them into solution, what happens? Just like with HBr, they all split apart. So I'm going to get out 3 total sodium ions and 3 total hydroxide ions. Again, we would say that the percent ionization is 100%. Now, strong acids and bases almost entirely dissociate, but it doesn't mean every single one will. So occasionally, if I put like 1,000,000 down into solution, maybe one will stay together. Okay, what about a weak base like NH3? Well, these do pretty strange things. If you notice, NH3 doesn't have any ions. Those are both non-metals, nitrogen and hydrogens. Turns out, though, that what they make in water is, if I react NH3 with water, they still make ions, because what happens is a hydrogen is grabbed by the NH3, and that makes NH4, which is an ion because it's positively charged, and OH minus. So this is a very strange way that weak bases work. But what weak bases do is they grab the hydrogens off of water and leave behind an OH. So if I put 3 NH3s into solution, what will happen is maybe one of them goes out and grabs a hydrogen and gives me NH4 plus and OH minus, whereas the other two stay together as NH3. So that's a little stranger, but that's what happens with my weak bases. Again, they basically partially dissociate. They partially split up. Some of them ionize. Let's look at their formal definitions. Here, we see that strong bases are bases that fully dissociate in water. And we have the example of sodium hydroxide, just like we did on the previous slide. So in purple, we have sodium, in blue, we have oxygen, and in white, we have hydrogen. And when I mix them with water, they just split apart into their ions. Weak bases are bases that sometimes dissociate in water. And here we'll take a closer look at what happens with that NH3 in water thing. If I have water, it turns out that nitrogen has some extra electrons right here that like to go out and grab a hydrogen. And so this hydrogen comes from water. So we take one hydrogen from water and go and attach it to nitrogen. What does that make? Well, that makes our NH4, Now it has an extra hydrogen and it's positively charged, and it leaves behind water, but it's missing a hydrogen, so it's OH minus. So weak bases are bases that sometimes dissociate in water, and sometimes they do that in pretty strange ways like this NH3 thing we see here. Okay, with that in mind, let's take a look at thinking about how weak some acid or base is. We can quantify that with what we call percent ionization, which we've already referenced. Here for bases, we see that percent ionization is equal to the concentration of hydroxide, so that's what's up here, the concentration of hydroxide, divided by B, which stands for base. So this is the concentration of base. What that means is if I put 1 molar of a base into a solution and it makes 0.1 molar OH in solution, then I would plug those numbers in and I would get a percent ionization of about 10%. We can do the same thing for acids. Here we put H+, what dissociates from an acid, on top, and HA, the original acid, on the bottom. Let's practice using these equations. Here we have a problem that says calculate the percent ionization for a weak acid with a concentration of 0.5 molar and a pH of 2.2. So the pH is given to us so that we can figure out H+. So ultimately, we're going to get H+ right here from our pH. HA, the concentration of the original acid, is actually given to us. It's 0.5 molar. Okay, so what are the steps here? Well, the first step is to determine H+ concentration with the pH equation. So here's my pH equation. And if you recall, to use that to find H+ concentration, I need to go ahead and multiply both sides by the -1. And when I multiply both sides by -1, I get negative pH equals log of my H+ concentration. And now to get rid of my log, I do 10 raised to both sides. So 10 raised to the pH and 10 raised to the log. And you may or may not remember from algebra 2 that that goes away. Okay, so then we get 10 raised to the negative pH equals my H+ concentration. And lots of people will just go ahead and memorize that equation so that they can easily go from pH to H+ concentration. All right, so that means 10 raised to the negative 2.2. Why 2.2? Because that's the pH. And what is that going to equal? It turns out, if you put that in your calculator, you'll get 0.00631. That has the units of molarity because it's a concentration, and that's equal to the concentration of our H+ ions. Okay, so now step 2 is calculate the percent ionization. Here's our formula for percent ionization, and we know the top, the numerator, is going to be what we just calculated, the concentration of H+, 0.00631. And we know the bottom concentration, that one was just given to us in our problem because we're told that the acid has a concentration of 0.5 molar. So we plug in 0.50 molar. And now the last thing we do is we multiply by 100. When we put that into our calculator, we will get 1.2%. 1.2%. Okay, so that's the percent ionization. Notice that means all of the acid actually stays together and just a little teeny bit falls off, which is what we would expect because we have a weak acid, which just partially dissociates. All right, last, let's practice identifying an acid or a base as strong or weak based on their percent ionization. So go ahead and pause the video for a second and try to guess from the percent ionizations below whether each one of those is a weak or strong acid. When we look at A, we see that 12% is the ionization. So that means 12% of them fall apart. That means most stay together, and that means that we have a weak acid. So a weak acid because the dissociation is quite low. 99.8, that one may have given you a little bit of trouble because you'd be like, I don't know, it's not 100%. But remember, strong acids almost entirely dissociate. We say fully dissociate. Occasionally, just a couple of them stay together, but that's almost 100%. So that's going to be a strong acid. So that's a strong acid. When we go to 5.05%, that's pretty straightforward. It's a pretty small dissociation percent. Most of them are staying together. And so we know that that is a weak acid. So there we have a weak acid. Lastly, we have 100%. All of it's dissociating. And there we very clearly have a strong acid because there's a 100% dissociation. All right. So what have we learned? We've introduced weak acids, we've introduced weak bases, and we've practiced percent ionization calculations. Hey, hey.